So let me just introduce you. So the next speaker is Sophie Morel from CNRS and INS Lyon that is going to speak about formalizing Grassmannians in Lean.
Yeah, wait, I didn't share what I wanted to share.
Sorry.
Yes, good. Oh, sorry, I should start. Where is it? Okay, yeah, so this is going to be more of a mass talk. Okay, so Grassmannians, so I'm going to start by explaining what is a Grassmannian. So it's a generalization of projective space. So you take a field or a division algebra, K, and take a vector space over K, and take a natural number R, and then the R Grassmannian is just the space of R-dimensional subspaces of E. Okay, so this is the green things are Lean code. So you can find on Zulip, I put a link to the Git repository where you can find all the code. Okay, so the case R equals 1, you just get the space of lines in E, so that's projective space of E. Okay. Now, if you go and you look at the definition of projective space in E, it's not in MATLib, it's not going to be the space of lines. It's actually what is called projectivization now, and it's actually defined as a quotient. So it's a quotient of a setoid, and a setoid is just you take non-zero vectors in E, and you take the equivalence relation that is, you can just take a non-zero vector, multiply it by a non-zero scalar. Okay, so that means that in mathematical terms, projective space is just E minus 0 divided by this homotopy relation. So you can do Grassmannians the same way if you want. So it's maybe a bit more concrete point of view. So you just define a setoid on the space of families of linearly independent vectors, are linearly independent vectors, and the equivalence relation is two families are equivalent if and only if they have the same span. Okay, so basically you have a R-dimensional subspace, you represent it by basis, and then you quotient out by the relation that two families are equivalent if they define the same subspace. So yeah, there's a this little I here, I use I instead of in R because you don't really want the families to be ordered in every case. So anyway, that's okay. So that's a Grassmannian. And so the question that I was asked by by Heather at the Lean conference is it possible to put the natural so there's a natural structure of a differential manifold on there. Is it possible to define it in Lean? I mean, of course it's possible, like it's possible for you to do it. So I'm going to remind you what a manifold is. So a manifold, basically, it's well, the very rough idea is a space that locally looks like an open subset of a vector space, like Rn, for example. So the example that we have in Lean that Heather formalized is the sphere. So if you look at the sphere and you look at the point of the sphere, you can see that locally around the point, the sphere looks like a plane. Okay. And so more formally, a manifold, it's a topological space M. So that means that you have a notion, if you don't know what a topological space is, just you have a notion of closeness on M, points being close to each other. And it's a family, it's what we call an atlas. So it's a family of charts on M. So the charts go from open subsets of M to open subsets of some vector spaces R to the Ni. And then you have two conditions on this atlas. So yeah, these charts have to be homeomorphism. So the two conditions is that first, the charts have to cover M. So M is the union of all these domains of definition. And the second important condition is that well, when I identify these open subsets of M2 open subsets in vector spaces, this should be well consistent from the point of view of C-infinity maps. So what we call the change of chart maps should be smooth. If you go from an open subset of R and I here by one chart, and then you go to by another chart to another R vector space, then it should be C-infinity. So I wrote the formal diagram, which is a little bit annoying. And by the way, this thing is what we call the model space of the manifold. Okay, so basically around every point you have a way to identify a neighborhood of that point to something open in R to the n, and then this has to be like there is this coherent condition. And manifolds in Lean, so there are two things that don't happen in mass that happen in Lean when manifolds are implemented. Is first the model space. Here I took R to the ni. In Lean, actually, it has to be fixed. So you couldn't have like the digital union of a line and a point that's not a manifold in Lean. Okay. They are also more general because we want to allow manifolds with boundaries or manifolds with corners, but I'm not going to talk about that today. And the second technical point is that when you define a manifold in Lean, you have to give for every point, you have to give a chart that is defined around that point. Okay, so that's just the definition in MATLAB. And then, yeah, here is the, is it easy to just change what? Okay, never mind. I wanted to show you MATLAB, but that will require non-trivial manipulation. Anyway, let's come back to the Grassmannian. So if we want the Grassmannian to be a manifold, we need to have some kind of topology on E. So I'm going to take the field to be a valued field. So you can think that it's R, for example. And the E is a norm space. So you can think it is R to the n. Is your favorite norm, like Euclidean norm. And then, so remember the Grassmannian, we have 2 points of view on it. We can say it's the R-dimensional subspaces of E, or we can say it's this quotient of families of R linearly independent vectors in E. And this set of families of R linearly independent vectors, so the linear independence is an open condition. So this is an open subset of E to the R. So already this thing that we quotient has a manifold structure because it's open in a vector space. And in particular, it has a topology. So the Grassmannian has a natural topology, which is just the quotient topology. And what we want is that we want this quotient map to be smooth. Like otherwise, our definition of the manifold structure is stupid. Okay, now I will show you what happens in finite dimension for the two Grassmannian. So I thought about showing you projective space, but projective space it is not general enough, so it's not clear how to generalize. If I show you R equals 2 and I explain it well enough, normally it's clear how to generalize to any R. Okay, so what do you do? So the Grassmannian, yeah, so I'm tired of just writing Grassmannian, so I'm just going to call it G here, right? G is the Grassmannian. And R is fixed at 2. So elements of the Grassmannian, so those are planes in R to the n. And planes in R to the n, you can, as I said, you can represent them by a basis. So a basis is 2 linearly independent vectors in R to the n. And I'm just going to write them as column vectors. So you get a 2 by n matrix. And the linear independence condition is that this matrix should have rank 2. Okay, and here there's a key that should have been an R. Okay, can I do anything about that? I can. So the equivalence relation is just you can multiply these matrices on the right by elements of GL2 of R, and that gives you the equivalence relation. Okay, this is doing linear combinations of these vectors. And so the rank 2 condition means that this matrix here, this 2 by n matrix, has a non-zero 2 by 2 minor. Okay, so the minors, so that means you choose a submatrix that is square of size 2. So that means basically you choose 2 rows of the matrix. So the minors are indexed by I and j, two numbers I and j between 1 and n. And so the set where the minor indexed by ij is non-zero, I would call it uij. Okay, and those, it's easy to show our open subsets of the Grassmannian. And now I'm going to show you how to define a chart on uij. So let's look at u1, 2. Is obviously if we can do that one, we can do the others. So what is U12 is like matrices like that, and then the top square is invertible, has a non-zero determinant. So what you do is that you take this matrix and then you normalize it. So if you know projective space, you would just have one column, and then the open I'm looking at would be the ones where the first coordinate is non-zero, and you normalize by dividing by the first coordinate. So this is just the generalization. You have two columns. The first square is non-zero, and you divide by this matrix. So you get a normalized form where the matrix starts with 1, 0, 0, 1. Everything, so this part is just like 2 times n minus 2 entries. Those are totally free because this matrix is already rank 2, so you can have anything here. And so this is going to be a representative of the same element of the Grassmannian. It's going to define the same subspace. It's going to have the same span. And in that form, it's unique. So there's a unique representative of that form. Simply because if you multiply by a 2 by 2 matrix on the right, you're going to, if the matrix is not identity, you're going to change this part. Okay, so what this is telling you is that on this open subset U12, you have a chart that is just, you take this V here, you normalize it, and then you send it to all these coefficients here, these remaining coefficients. So the chart goes from U12 to R to the N, R to the 2 times N minus 2, and it's a homeomorphism. Okay, so this is a very nice case. The charts actually don't land in open subsets of this. It just the target is just the whole space. Okay, and then if you want this to define a manifold structure, you have to check that change of chart is smooth. So what happens if you move between charts? So here you have something in U12. I put it in normalized form, and suppose that it's also in U34. So the next two rows also define an invertible 2 by 2 matrix. How do I go to the other chart? Well, I have to divide by this 2 by 2 matrix. So I take this thing and I multiply it by the inverse of this. But this, in the entries of V prime, this is a smooth operation. I'm just doing, well, I mean, this inverse is just like the transpose of the core matrix divided by the determinant. So these are all rational fractions of the coefficients without poles on the domain of definition. Okay, so this is all very nice, but as you all know, when we formalize something in mean, we don't want to use coordinates. Also, my E could be infinite dimensional. Okay, so I don't even have coordinates in general. So how do you do the coordinate-free version of that? Well, it's very easy. So what did we need to define a chart? So we needed to have this notion of 2 by 2 minor. So we need to have like 2 coordinates on the vectors of E. Okay, so like this top 2 rows. And then we need to be able to talk about the rest, like what's left of my vectors once I fix these first 2 coordinates. So like the remainder of the vector. So what that means is that I actually need a decomposition of E into a component K square and then a supplement. So it's an isomorphism between E and K squared times some other normed vector space U. So these are going to be what parameterize the charts. This isomorphisms phi between E and K squared times U. Then what is the domain of definition of the corresponding chart? So it should be the subspaces where a basis is sent to a basis of this K square here. 2 linearly independent vectors in this K square. That's the non-zero minor condition. Okay, so what does that mean? It means it's the subspaces W, where if I restrict the first component of phi to W, I get an isomorphism. For dimension reasons, this is dimension 2, this is dimension 2. So being an isomorphism is the same as being surjective, it's the same as being injective. So I wrote it like that again. W intersects the kernel of phi1 trivially. And you can check this is an open condition, okay? Now, what is the chart? Well, this is also, so how do you write the chart? Well, okay, so if you have this thing here, right, what is going to be this 2 by 2 matrix? This is like the matrix of phi1. And what is the rest here? This is like the matrix of phi2. Well, this is phi1 on W. This is phi2 on W. And this is the matrix given by the basis of W I have chosen. So what did I do to get the chart? I took this part, the matrix of phi2, and I divide by this part, the matrix of phi1. So the chart is just phi1 times the inverse of, phi2 times the inverse of phi1 when everyone is restricted to W. So here it is. Right, it's here. Okay, and this is just, what is this? This is a continuous linear map from K square. This one here, I lost my, here. This one goes from K squared to W, and you compose it by this one that goes from W to U. So it's a continuous linear map from K squared to U. And if you want to think of the two column vectors from before, those are the images of the canonical basis of K squared. But it's nicer to think about continuous linear maps, I think. Okay? And if you want to show that something is a homomorphism, you need to show that its inverse is continuous. So we need a formula for the inverse of the chart. And if you think about it a little bit, well, so you have to start with a continuous linear map from K squared to U, and you have to construct a two-dimensional subspace of E. And you are given an isomorphism between E and K squared times U. So what do? You have a map like this. So you take its graph, that's a two-dimensional subspace in this product, and then you pull it back, right? That's the only reasonable thing you can do, and so it works, of course. So when you actually implement that in Lean, I don't know if I can show you maybe the code at the end, it actually helps to lift everything to the this set that we have, this like, right, this set of vectors. So you can define the lift of a chart and the lift of the inverse when you want to show that things are actually continuous maps. But then it's pretty easy because all the maps, it's just a combination of either continuous linear maps or taking the inverse of an invertible map, which is known to be a continuous operation that was already in MATLAB. Anyway, there are a few, change of charts is not that hard. There are a few issues. Some of the issues are because of the way MATLAB is written, and some of the issues are because of mass itself. So one issue is I didn't talk about the model space. So what is the model space for this chart defined by phi? And phi is this isomorphism here. Oh, by the way, I have 2's everywhere, but now you can just replace 2 by R and nothing changes. So the model space is the space of linear maps, continuous linear maps from K squared to U. So if you're writing in Lean, it looks like this. And it depends on U. And what is U? If you look at that, what is U? U is just a two codimensional subspace of E, right? So there is no canonical choice. They are all isomorphic, but there is no canonical choice. So you use the axiom of choice to pick one, which made people very unhappy when I talked about that on Zuli, but there is no way around that, unless you are finite dimensional, which you don't really want to be. The second issue is you need to pick a chart at around each point of the Grassmannian. And again, there is no natural choice for a chart. There are many, many, many choices that work. So again, axiom of choice to pick one. And the third issue, which I didn't mention until now, because I was pretending that we are finite dimensional, is that you need charts to exist. So you need to have two codimensional subspaces of E, and that is not always true. Of course, if you're finite dimensional, it's true. And actually a necessary and sufficient hypothesis for that is for the continuous dual of E to separate points. So you need to put this separating dual instance of E on E. And then there is a small lemma that says you're going to get subspaces of any codimension, which I also have written. Okay, so this is okay if you're over R or C. This is okay by Han-Banach. If you're finite dimensional, this is okay. If you're the dual of another space, this is also okay. So you get the actual algebraic geometry Grassmannian. The Grassmannian of the dual is the space of R-dimensional quotients of E. So that's the one that I like. Anyway, okay, now that you are very happy, you have this manifold structure on the Grassmannian, what can you do with it? I mean, you need to be able to prove that some maps are smooth. So how do you do that? Well, remember, the Grassmannian is a quotient of this thing, which is just independent families of independent vectors in E to the R, and this is open in E to the R. So this is a manifold. This one's a manifold in some trivial way. So of course, well, so you want this pi to be smooth, but you want more actually. If you have a map from F from the Grassmannian into another manifold, what you want is that F is smooth if and only if F composed with pi is smooth. And actually, you also want to be able to, I mean, I also wrote a product version where this is sometimes times the Grassmannian into sometimes times M, something times M. And actually, if you look at the code, what is proved is local versions, so something around each point of the Grassmannian. Like you have a point to the Grassmannian, you have a lift here, then this F is smooth around the point if and only if F times pi is smooth around the lift of the point. And this allows you to do things pretty easily. For example, you can define the action of the group of automorphisms of E on the Grassmannian. So these are automorphisms as a topological vector space. So this is what some people also call GLE. It acts on the Grassmannian because if you have an automorphism of E and an R-dimensional subspace, you can just take the image of the space by the automorphism. And this is a smooth operation from what E cross the Grassmannian to the Grassmannian. And the second one, the big one, is the Plücker embedding, which I have 2 minutes to define. So what is the Plücker embedding? Okay, so I have 2 minutes, so I can pretend everybody knows math very well. Skip the example. You have the Grassmannian, you have an R-dimensional subspace. You take its R exterior power, you get a line into the R exterior power of E. That's called the Plücker embedding. Is very, very important when you study Grassmannians. And I wanted to be able to define that and prove it smooth. So here are all the issues. First, exterior powers are defined in MathLib, and there is nothing else. So you need functoriality of exterior powers to be able to say that this is a subspace of the exterior power of E. You need the dimension formula for exterior powers to be able to say that this is dimension 1, etc. Second, you need the exterior power to be a norm space. Otherwise, you won't have a manifold structure on the Grassmannian. But there are several possible norms. So I chose one, if you're an expert, that's the epsilon norm. Okay, so the one that makes the exterior power is dual should be the space of continuous alternating maps on E. But continuous alternating maps are not in MathLib, so you also have to implement them. Third, once you have defined a Plücker map, you want to prove it smooth. How do you prove it smooth? Sorry, you lift it here. When you lift it, it becomes a canonical continuous alternating map. We do not know that continuous alternating maps are smooth in MathLib, so you have to prove that too. Okay, and that's the end. So here's the to-do, all the things that I would like to do but haven't done. First, the norm on the exterior power is kind of crappy because you only get the universal property for maps into K itself. I would like it for maps into any non-K vector space. So I know how to do that, but there will be problems with universes. The Grassmannian is compact if E is finite dimensional and K is locally compact. It would be nice to prove that. The Plücker map, it's known to be injective, a homeomorphism of its image. The equations of the images are known. I have not implemented that yet, the Grassmannian, of course, has a tautological rank R vector bundle because it parameterizes R-dimensional subspaces of E. It has a universal property, actually has several universal properties. And then there are all the smooth maps, mostly on projective space, that you would like to be able to define. Okay, and then this is like kind of a joke, because before you can define that, you need to have know way more things about flatness in lane. I don't think we have that yet. Thank you.
Okay, thank you. Thank you very much for the talk. So any questions? So I see a question from Kevin.
So what do you need from flat? I have a PhD student developing the theory of flatness.
Yeah, well, ideally you don't want to define a Grassmannian, right? You want to define chord schemes. So
Yes. Okay.
anyway, yeah, I haven't made a list of what you need for flatness because I haven't thought seriously about doing chord schemes in India.
Yeah. That would be a great project, chord schemes. Thanks. Very nice talk, by the way. Thank you.
Sure, thanks. But I don't think there's a lot in MATLAB. I think people have projects but about properties of flat modules, but I don't know if there's a lot in MATLAB yet.
Yeah, right. It's on the way to MATLAB.
That's good.
And I also see a question from the Hoskinson Center, maybe Patrick, or I don't know.
Yeah, I got a question. So thanks, Sophie, for this talk. It was very nice. I wonder, did you learn any new mathematics while you're working on this, especially around the infinite dimensional case, maybe?
Well, I mean, I guess the norm. So the norm on exterior powers. Yeah, I didn't know much about like norms on. Well, I mean, I'm supposed to know about norms on, vector spaces, tensor products of norm vector spaces. I know there's this construction of Grothendieck. I know there's these two extremes that are called epsilon and pi, but I hadn't really manipulated them very much. So that was probably the strangest thing for me.
Okay, but this is not changing the way how you think about Grassmannians if you need to teach this again in a differential geometry class or something.
Well, I don't teach differential geometry. I teach algebraic geometry. Yeah. And I guess, yeah, if I teach algebraic geometry, I think if I tell the students about these charts without the coordinates, they will be very confused. Well, I don't know what you think about
But this is a very elegant way of doing it, though. That was why I liked the talk.
Of course, the formulas are much simpler, actually, than the ones with coordinates.
But there is even with less coordinates, you can just talk about a fixed codimension R subspace, and the chart is the set of subspaces that are transverse to this coordinate subspace. So
yeah, I mean that's basically what you are doing, right?
Yeah, but I mean you can present it in an even more abstract way if students are not confused enough.
Yeah, great. But you have this problem that whoever wrote Manifolds in Lean wanted a fixed model space, and I'm sure they had very good reasons.
Maybe Sebastian is around and can comment on that.
But that's kind of like making the construction a bit less natural.